Hello everyone. Today I am going to present my video on OpenMP, the OpenMP AI specification for parallel programming. So here I am, Arushi Vij from EB15 having enrollment number E20CSC 325 from Bennett University batch 2020 to 2024. So what is it? What is OpenMP? So OpenMP is a open multiprocessing is an application programming interface API that supports multi-platform shared memory multiprocessing programming in various languages such as C, C++, and Fortran on many platforms, instruction set architectures and operating system including Solaris, AIX, FreeBSD, HPUX, Linux, macOS and Windows. It consists of a set of compiler directives, library routines, and environment variables that influence runtime behavior. OpenMP is managed by the non-profit technology consortium OpenMP Architecture Review Board or OpenMP ARB, jointly defined by the broad swath of leading computer hardware and software vendors, including ARM, AMD, IBM, Intel Cray, HP, Fujitsu, NVIDIA, NEC, Red Hat, Texas Instruments, and Oracle Corporation. OpenMP uses a portable, scalable model that gives programmers a simple and a flexible interface for developing parallel applications for platforms ranging from the standard desktop computer to the supercomputer. An application built with a hybrid model of parallel programming can run on a computer cluster using both OpenMP and message passing interface MPI, such that OpenMP is used for parallelism within a multi-core node while MPI is used for parallelism between the nodes. There have also been efforts to run OpenMP on software distributed shared memory systems to translate OpenMP to MPI and to extend the OpenMP for non-shared memory systems. So let's go in history and explain. I will explain you the history in brief. The OpenMP Architecture Review Board ARB published its first API specifications OpenMP for Fortran 1.0 in October 1997. In October the following year, they released the C or C++ standard. 2000 saw version 2.0 of the Fortran specification with the versions 2.0 of C or C++ specifications being released in 2002. Version 2.5 is a combined C or C++ Fortran specification that was released in 2005. Up to version 2.0, OpenMP primarily specifies ways to parallelize highly regular loops as they occur in matrix-oriented numerical programming, where number of iterations of the loop is known as the entry time. This was recognized as the limitation and various parallel extensions were added to implementations. In 2005, an effort to standardize task parallelism was formed, which published a proposal in 2007, task inspiration from task parallelism features in Silk, Extend, and Shaple. Version 3.0 was released in May 2008. Included in the new features in the 3.0 is the concept of task and the task construct, significantly broadening the scope of OpenMP beyond the parallel loop constructs that made up mostly of OpenMP 2.0. Version 4.0 of the specification was released in July 2013. It adds to improve the following features: support for accelerators, atomics, error handling, thread affinity, tasking extension, user-defined reduction, SIMD support, Fortran 2003 support. The current version is 5.2 released in 2021, which is kinda recent. Note that all the compilers that support full set of features for the latest versions. So OpenMP programming model. So I will explain you about it in brief. So OpenMP is an implementation of multi-threading, a method of parallelizing where a primary thread, a series of instructions executed consecutively, forks a specified number of subthreads and the system divides the task among them. The threads then run concurrently with the runtime environments allocating threads to different processors. The section of code that is meant to run in parallel is marked accordingly with a compiler directive that will cause the threads to form before the section is executed. Each thread has an ID attached to it which can be obtained using a function called OMP_GetThreadNum. The thread ID is an integer and the primary thread ID has an ID 0. After execution of the parallelized code, the threads join back to the primary thread which continues onward to end of the program. By default, each thread executes the parallelized section of code independently. Work sharing constructs can be used to divide the task among the threads so that each thread executes its allocated part of the code. Both task parallelism and data parallelism can be achieved using OpenMP in this way. The runtime environment allocates threads to processors depending on the usage, machine load, and other factors. The runtime environment can assign the number of the threads based on environment variables or the code can do. So using functions, the OpenMP functions are included in header file labeled as OMP.H in C or C++. So what was the goals? Standardization. Provide a standard among variety of shared memory architectures or platforms. Lean and mean. Establish a simple and limited set of directives for programming shared memory machines. Significant parallelism can be implemented by using 3 or 4 directives. Ease of use provide capability to incrementally parallelize a serialized program. Unlike message passing libraries, which typically require all or nothing approach, provide the capability to implement both coarse-grained and fine-grained parallelism. Nested parallelism support the API provides for the placement of parallel constructs inside of other parallel constructs. Implementation may or may not support this feature. Next is the shared memory thread-based parallelism. OpenMP is based upon the existence of multiple threads in the shared memory programming paradigm. A shared memory process consists of multiple threads. So, OpenMP core elements. The core elements of the OpenMP are the constructs for thread creation, workload, distribution, data environment management, thread synchronization, user level routines, and environment variables. In C or C++, OpenMP uses hashtag paragons. The OpenMP specific paragons are listed here. So let's discuss the important fork join model. All the MP programs begin a single process, the master thread. The master thread sequentially executed until the first parallel region construct is encountered. So what is fork? The fork is the master thread then creates a team of parallel threads. The statements in the program that are enclosed by the parallel region construct are then executed in parallel among the team of threads. Join. When the team threads complete the statements in the parallel region construct, they synchronize and terminate, leaving only the master thread. So I will discuss the core of MPI. So first is the thread creation. The pragma OMP parallel is used for the fork additional threads to carry out the work enclosed in the construct in parallel. The original thread will be denoted as master thread with thread ID 0. So here is the small diagram, and you can see that the parallelism added incrementally until the performance goals are met, and the master thread spawns of the team of the threads are needed. So here is a small example using flag f open mp to compile using gcc output on the computer with 2 cores, and thus there are 2 threads. In the output you can see 2 hello world because there are 2 threads. However, the output may also be garbled because of the raised condition caused by the 2 threads sharing the standard output. Here is a small code. You can see that the parallel region with the default number of threads are shown by hashtag pragma omp parallel. OpenMP include files is omp.h and end of the parallel region. This bracket signifies that the parallel region has been ended, and that thread num signifies the runtime library function to return a thread ID. And we know that the first thread ID would be 0. It is by default. Next is the work sharing constructs. It is used to specify how to assign independent work to one or all of the threads. OMP4 or OMP2, first is that, used to split up loop iteration among the threads, also called loop constructs. Second is sections, assigning consecutive but independent code blocks to different threads. Single specifying a code block that is executed by only one thread. A barrier is implemented at the end. Master similar to single, but the code block will be executed by the master thread only. No barrier is implied at the end. Here is a small example. First of all, initialize the value of the large array in parallel and each thread to do the part of the work. This example is embarrassingly parallel and depends only on the value of I. The OpenMP parallel for flag tells the OpenMP system to split this task among its working threads. The threads will each receive a unique and private version of the variable. For instance, with 2 worker threads, one thread might be handed a version of I that runs from 0 to 49,999, while the second gets a version running from 50,000 to 99,999. Next is the variant directives. Variant directives is one of the major features introduced in the OpenMP 5.0 specification to facilitate the programmers or developers to improve the performance portability. They enable adaptation of OpenMP paradigmas and user code at compile time. The specification defined traits to describe OpenMP constructs, execution devices, and functionality provided by an implementation. Context selectors based on the traits and the user-defined conditions, and meta directive and declare directives for users to program the same code region with variant directives. So the meta directive is an executable directive that conditionally resolves to another directive at compile time by selecting from multiple directive variants based on the traits that defined an OpenMP condition or context. The declare variant directive has similar functionality as meta directive but selects a function variant at the call of the site based on the context or user defined conditions. The mechanism provided by the two variant directives for selecting variants is more convenient to use than the C or the C++ preprocessing since it directly support variant selection in OpenMP and allows an OpenMP compiler to determine the final directive from the variants and the context. Here is a small example where you can see that the first is the code adaptation using pre-processing directives. Here, Pragma OMP target teams distribute parallel for map and hashtag Pragma open target parallel for map to V1 to V2 map from V3. This is the code adaptation using pre-processing directives, and the second is the code adaptation using meta directive in the OpenMP 5.0. So these are the two examples, and you can distinguish between the pre-processing directives and the meta directives from this. Next is the synchronization, which is like since OpenMP is a shared memory programming model, most variables in OpenMP code are visible to all the threads by default. But sometimes private variables are necessary to avoid race conditions, and there is a need to pass values between the sequential part and the parallel region. The code block executed in parallel, so data environment management is introduced as data sharing attribute clauses by appending them to the OpenMP directive. The different types of clauses are here. Critical. The enclosed code block will be executed by only one thread at a time and not simultaneously executed by the multiple threads. So this was the critical part. It is often used to protect the shared data from the race conditions. Second was atomic. The memory update, written or like read or modify write in the next instruction will be performed atomically. It does not make the entire statement atomic, only the memory update is atomic. A compiler might use specific hardware instructions for better performance when using the critical ordered. Next is ordered. The structured block is executed in order in which iterations should be executed in the sequential loop. Next is the barrier. Each thread waits until all the other threads of the team has reached to the point. A work sharing construct has an implicit barrier synchronization at the end. And the last is the now wait, specifies that threads completing assigned work can proceed without waiting for all the threads in the team. So, environment variables. This is the last code. The method to alter the execution features of OpenMP applications used to control loop iterations, scheduling, default number of threads, etc. For example, OMP hashtag num hashtag threads is used to specify the number of threads for an application. Whenever it's mentioned in the code, we just have to write. We should know that it is specifying the number of threads that we are using in the application because threads are kind of very important in the parallel programming. And next, I want to discuss difference between exclusive and directive based programming. So directive layered on the top of threads facilitate a variety of thread related tasks. A programmer is rid of the task of initializing attributes, objects, and setting up arguments to threads, partitioning iteration spaces, etc. There are some drawbacks to using directives as well. An artifact of explicit threading is that data exchange is more apparent. This helps in alleviating some of the overheads from data movement, false sharing, and contention. Explicit threading also provides a richer API in the form of condition weights, locks of different types, and increased flexibility for building composite synchronization operation. Finally, since explicit threading is used more widely than OpenMP, tools and support for p-threads programs are easier to find in this. So this is a small difference between the two, the directive and the exclusive one. So like it's easy to understand from this. So at the end, I want to just end my video. Thank you for listening to the video and having patience for listening it. Thank you.